light itself has an intrinsic grain, and that is you can take an image at very high resolution, but if you keep blowing it up and magnifying it more and more, you don't actually get more information. And I'd like to talk about why that is, because this has limited traditional forms of microscopy with a limit that's related to the diffraction of light, and I'll explain what that is. And this diffraction limit ultimately leads us to an irresolvably small spot of light, which is based on something known as the point spread function, that limits the resolution of traditional forms of microscopy. So to begin, I think we have to talk about why light doesn't behave in a way that just would allow infinite magnification. And that is that for most of us, anyone who's held a laser pointer, you get the impression light travels in straight lines, and that it should be very straightforward to understand where light goes. And the best example of this for imaging is the simplest of all imaging devices, the pinhole camera. And I just want to show you a picture of a pinhole camera here. Pinhole camera is a device that has a box, and this box has a pinhole in it, and the box usually has a piece of photographic paper inside the box. The box is sealed. I've not shown the sides of the box. And the photographic paper is looking at the world, and the world is being seen through a single pinhole. And in this case, the world consists of a single lamppost shown over on the side of this image. And the idea of the pinhole camera is very straightforward. It's that light from each part of the lamppost goes in all directions, but because the pinhole is only in one place, only one ray of light from each part of the lamppost gets through the pinhole. So the very top of the lamppost has light going in many directions. The two dotted lines are two directions light is traveling that bumps into the wall of the box, but one of the rays, the one that's solid, goes through the pinhole and ends up down here. Similarly, light from the bottom of the lamppost goes in all directions, but the only light that passes through the pinhole is the part that ends up here. And so it goes for every object in space. And so if you leave the photographic paper inside a pinhole camera long enough, you get a very nice picture of the world. And if this were the way light actually acts, then we should be able to do very high resolution, because light just travels in straight lines, and we should be able to expand objects. For example, if we move the piece of photographic paper farther away from the pinhole, that object gets bigger, and it should get bigger and bigger and bigger, and we should get more and more resolution. So that ultimately every little fact of life in the real world should end up on that piece of paper. It turns out, however, that there are certain problems with the pinhole camera, and that is which limits its resolution. And I want to give you one obvious example. You can see that if the pinhole were bigger, this image would get fuzzy because there would be more than one ray of light from the top of the lamppost that would get through the pinhole, and it would blur the image down here. So a big pinhole wouldn't work at all. In fact, if there was no pinhole at all, you wouldn't get an image of the world. You just get light on this piece of paper. However, you might imagine we should get better resolution if we turned the pinhole down. It would be a sharper image as the pinhole got smaller and smaller, restricting only a single ray of light from each position from getting through. But the surprising thing about a pinhole camera is that if you make the pinhole very small, as shown here, so now that only a very infinitesimally small amount of light gets through, then suddenly the image gets blurry again. And this blurriness ultimately is because light is not traveling in straight lines. Light is bent at that pinhole. It's diffracted, and that bending of light is ultimately what limits the light microscope. So I want to explain why the light bends, because I think if you understand why the light bends, you'll understand why microscopes have limited resolution. It bends because light is actually not traveling in straight lines, despite the fact it seems to. It's actually that light is a wave, and it's traveling in all directions. This is not an intuitively obvious idea for most people. In fact, it required a great genius, a man named Christian Huygens, to first figure out this fact. Christian Huygens was a Dutch polymath. He did many, many things, invented many things. He was a genius in many different areas. And one of his great claims to fame was wave optics, the idea that light travels in waves, not in lines. This was his big idea, and it was counterbalanced by Newton's brilliant idea that light is actually made of particles, the corpuscular theory of light. And of course, we all know about photons, and that word photon was first used by Newton. It turns out they were both right, and in some ways, Christian Huygens was closer to reality, I think, than Newton's view of light. But that's a long story. I want to just tell you what a wave theory says light actually is. Instead of being a straight line, that light can be thought of as traveling as a wave. And a wave might be thought of as a straight plane wave. And by a plane wave, you would have a front of light moving in a particular straight direction, as these arrows say. And that wave front, it would be like the breaker at a beach, a long linear wave moving forward, and right behind it, at its wavelength, is another wave, and behind it is another wave. So each of those vertical lines consists of one of these waves. And right below that little sinusoid is a way to represent in 2 dimensions just the direction of the wave. The wave is waving up and down, but the light is moving left and right. It's called a plane wave because, in fact, it's not a single line moving, but it's actually a plane waving, and right behind it another plane waving. So that's why it's called a plane wave. Wave optics says that in addition to plane waves, light can travel in directions that either converge to a point or diverge, and these are known as spherical waves, where the wave front, rather than being a straight line, is now a curved surface. It could even be a sphere, in which the light is traveling out from a single point or converging in towards a single point, and there you might draw it that way. So spherical waves are the curvature of a circle or a sphere, and plane waves are the surface of a plane. Now, Huygens' idea was that the elemental unit of light was not these plane waves, but the plane waves and the spherical waves were composed of very small, infinitesimally small objects that now are called Huygens wavelets, which are little points of light that distribute their light in all directions, that have no directionality at all. He called these wavelets, and to this day we use that term wavelet. And many aspects of the way a photon behaves in space before it interacts with matter is very much like a Huygens wavelet. That is, the light is traveling in all directions, and where it ends up has a lot to do with where there's no interference, as opposed to where it doesn't end up are sites where light is interfering. And I'll explain that in a second. So a Huygens wavelet can be thought of as a pulsating little point of light. I'm showing here sort of a diagram of that pulsation, where there would be a point of light, and that pulsation, that is sort of the fluctuation of the wave, where the distance between the crests of these waves are basically the wavelength of light. This is the unit of light. It's an infinitesimally small unit, and shorter wavelength light has the spacing closer together and the frequency of the pulsing higher. At any instant in time, a wavelet might look as shown on this side, on the left here, with a series of rings, each of which have the same amount of energy, but because each ring is larger, the amplitude of the wave gets smaller and smaller as one goes out at any one point. The intensity one sees is the square of the amplitude of the wave, and then one has to integrate that over at least one wavelength. So one has a very bright spot and then progressively dimmer light if you integrate the effect of a wavelet over time. So how do these wavelets explain plane waves and spherical waves? That's easy to see by Huygens' original drawings, and here's a more modern version of these drawings, which is that a plane wave, shown in this diagram, is just a series of wavelets that are aligned in a straight line, as shown here. And those wavelets have a leading edge, which is the wavefront of each of them, and that a line of those leading edges gives a straight line, and in that direction there's nothing to interfere with them, so that moves forward, and the next wavelet, the next wave comes right behind it. Spherical waves are a similar idea, but rather than being a straight line of wavelets, the wavelets are on the surface of a sphere, And they can either be diverging, so the light is leaving a point, spreading out in space, or converging, as occurs, for example, when a laser is focused to a spot in a specimen. Beyond the spot, the light rediverges, so a converging spherical wave generates a diverging spherical wave. So there are spherical waves and plane waves. Now, how does this help us understand why a pinhole, when it gets small, not work, is explained here. That if you have a very, very small opening, and you have a plane wave with a bunch of wavelets lined up underneath that pinhole, that if the hole is very small, only a few or maybe even one wavelet gets through, and that wavelet then spreads its light out in all directions. And that is what is known as diffraction. And that diffraction explains why if the pinhole gets very small, the light no longer travels in a straight line. It bends in all these different directions. And this is a theoretical approximation, and yet all experiments suggest this is actually the way light behaves. Now, one interesting thing is if you have two wavelets or more that came from the same source, that are part of the same original pulsating light, and therefore they are coherent, their wavelengths are in sync with each other, then one can have interference patterns made up of several wavelets. So first, in the example with one pinhole, light in a box will be going in all directions, but the light coming out will bend. That is diffraction. And then in a second example, if one has more than one source, for example, a light source that then goes through two slits, one sees out at the other end, rather than just uniform light, a funny banding pattern of destructive and constructive interference. The light goes through one pinhole, and then after it goes through two more pinholes, you get this weird interaction of places where the crests are on top of each other, where the troughs are adding together in a negative direction, and places where one is a trough and one is a peak, and they nullify. And so here in instantaneous time is a complicated pattern of waves based on the interactions of two different wavelets. And I want to unpack that idea a little more so you can understand how light microscopes work. So if we have a light source, as shown, that's sending out its light in all directions, and then that generates a spherical wave made up of a bunch of wavelets, one of the wavelets might go through a slit here and generate a pattern of a wavelet on the other side of that pinhole. There's a second slit in that box, and there's a second wavelet that's gone through. And together, those wavelets interact in ways that either add or subtract from each other. And there is that interaction pattern. So let's look at that pattern in a little more detail. If we go to a position where the two wavelet openings are exactly equidistant from that point, then they will both be cresting or troughing at that distance. And so one would have constructive interference. If we go to a position where one of the distances is exactly half a wavelength longer than the other, one would have destructive interference. So there would be bright light where they constructively interfere and no light where they destructively interfere. And that's why one ends up with this pattern of bright and dark bands. Because one can be even a whole wavelength apart, one can be one wavelength longer than the other, and still you would get constructive interference. But if it's 1.5 wavelengths difference in path length, then one would be destructive relative to the other. So one has light and dark bands that go over a wide range here. So how does this help us understand microscopes? Well, let's review for a second the way a microscope is designed. So a microscope takes light from a specimen, shown over here, and in this case there's just a single point of light generating a spherical wave. And what the microscope objective does is that point source, which generates a spherical wave that diverges, the objective lens then collects a sub-portion of that spherical wavelet and turns that light into a plane wave, because a microscope is designed such that the specimen plane is exactly at the focal distance of that lens. So spherical waves turn into plane waves. And those plane waves then travel through the microscope tube until it reaches the tube lens, which is another positive lens, which now takes a plane wave and turns it back the tube lens does this, turns the plane wave back into a converging spherical wave. And that spherical wave ends up as a point there. And this allows us to ask the following question, which is, for a point object in the focal plane, such as an infinitesimally small fluorescent bead, what is the distribution of light in or near the image plane? How is that point spread? Is it spread, first of all? And if it's spread, what is the function of that spread? How does it end up being a particular distribution? So we're going to go through the same idea of wavelets, but now look at it in this case of a converging spherical wave. We're going to look at that part of the microscope because that is where the interference patterns generate a complicated mix of focus to a point plus light around that point. So this is now beyond the tube lens. The tube lens is shown at the very extreme end of this image. There's a converging spherical wave made up of a bunch of wavelets, and each of those infinite points in the emerging wavefront is acting like its own point source of light, like a Huygens wavelet. That is, each point emits a wavelet, sending out light in all directions, and all wavelets from the same wavefront are mutually coherent. They're oscillating in synchrony. And because of that, they can interfere in a fixed way. Therefore, they interfere with each other in a very predictable pattern. So let's start now with just two of those wavelets and arbitrarily pick a position midway between them, where that vertical line is, where the distance, d1 and d2, are identical. The distance is the same. Those two waves will both be troughing, peaking, or in between at exactly the same point. And therefore, if you add those two waves together, they're in phase and you will get constructive interference. In distinction, d1 and d2 slightly lower down on that vertical line, one of those distances is now a half a wavelength longer. The top one, d1, is a half a wavelength longer distance than the bottom one, d2. And so when those two waves reach that point, they're out of phase, exactly half a wavelength out of phase. And if you add up those two sinusoids, you're going to end up with complete destructive interference and no light. If one goes a little further down, now d1 is much longer than d2. In fact, exactly one wavelength longer than d2. You add up those two waves, you're going to get a full cycle out of phase, but they are peaking at the same point, and that generates constructive interference. And so here is the patterns one sees instantaneously on the top and integrated over time on the bottom. And you can see that the troughs and the peaks of interference on the top have all turned now into positives and zeros. There's no negative amplitude when you square the amplitudes. Now everything is positive amplitude or zero, and that interference pattern ends up with a series of bands. So at an instant in time on the top, there's a mesh of dark and bright lines. Detectors, including the eye, however, don't see amplitude. We collect intensity. And intensity is the addition of a full cycle of those wavelets and squaring the result. And the detective interference pattern now has dark and bright lines. And right in the middle, there's a white line running horizontally. And that is the place where the two wavelets are mutually constructively interferencing all the way along that length. The dark areas are the destructive interference. The bright areas are the constructive interference. Okay, so we've dealt with two wavelets. And now I just want to say a little bit about the way microscopes work in the sense that there's nothing so far in what I've said that would tell you where the image plane for those converging spherical waves are. There's just a pattern of light and dark bands. You're going to see that this approach, without any extra understanding of ray optics, generates the image plane at a particular plane, largely because that is the one place where all the wavelets can be in phase at the same time. But before talking about that, we have to deal with the fact that microscope objectives come in many flavors, and the particular flavor I want to talk about now is not the difference in magnification, which many beginning microscopists think is the most important aspect of an objective. It isn't. What really matters for the quality of an objective and its resolving power is its numerical aperture, NA. And the NA has a weird description. It is the index of refraction of the material between the microscope objective and the slide, which in air would be very close to 1.0, but in water or glycerin or oil, that number could be higher, times the sine of the half angle between a vertical and the largest deviation of light that could still be collected by the objective. So a low numerical aperture lens, as shown in A, has a narrow cone that it can collect of light coming off of the specimen. So if you have a fluorescent specimen that sends light in all directions, you only collect a small amount with a low numerical aperture lens. A medium numerical aperture lens has a slightly larger cone that it collects, and a high numerical aperture lens has the highest cone of all. It is a fact, and I'll try to explain why, that the higher the numerical aperture is, the better the resolving power of the microscope. And we have to go back to that wavelet picture and look at the difference on the top between a high numerical aperture objective and on the bottom a low numerical aperture objective. So in both cases we have a wavelet generating light, and you see you're collecting a greater portion of that spherical wave with the high NA lens. So a larger amount of the light is collected, and that generates a larger, basically a bigger plane wave that eventually goes to the tube lens, and then from the tube lens it's converted into a converging spherical wave. So with a high numerical aperture lens you have more of the spherical wave collected, and so you generate a larger spherical wave going out towards the image plane. With a lower numerical aperture lens, you have a smaller amount of the spherical wave collected, and the edges of that spherical wave are very close together relative to a high numerical aperture lens, where the most extreme parts of the spherical wavelet that's converging are far apart from each other. And that turns out to be the critical feature for resolution, as you'll see. So if we compare the extreme wavelets from a curved spherical wave in a high numerical aperture lens and a low numerical aperture lens, you can see that the effect of that is a different pattern of banding down at this arbitrary position here, which will be the image plane, but there's nothing yet to tell you why, because two wavelets doesn't focus on an image. So the finest fringes determines the finest detail that can be found in an objective. This is what limits the resolution of the image, how fine that banding pattern is, and that period, that is the distance between the bright and dark areas, is related to the numerical aperture. If the two wavelets are far apart, then interference allows a very high frequency set of dark and light bands. If the two wavelets are very close together, as in a low numerical aperture lens, then the banding is more spread out. And this limits the finest detail in the image plane. So now let's try to not just look at two wavelets, but add more and more wavelets to that converging spherical wave, and look what happens to the integrated pattern of interference down at a plane that ultimately becomes the image plane. So first, high numerical aperture gives short fringe period and gives narrow fringes. Low numerical aperture gives long fringe period and wide fringes. So now, whatever numerical aperture we have, we're going to have a converging spherical wave. That's that blue circumference one sees at the top of this image. The tube lens is up above. And now what I'm showing you is the two wavelets at the rim of the lens plus one wavelet right at the center. So three wavelets are interfering, and we're looking at the pattern that is generated by these three wavelets after we integrate over a wavelength and square the result. The recorded intensity is a series of bar patterns. It turns into islands. Instead of that stripes, we now have islands of bright and dark. And at the image plane, which will end up where this line is here, one sees that there is an island of bright right in the center, and that is because at that point there you are equidistant from those three wavelets, because that point is the center of a circle for which those three wavelets are on the circumference of that circle. So they're equidistant from that point, and that is why, that is where the image is focused, for a point in the specimen that's located in the center of the image field. And the brightest light is there because the interference pattern is strongest, because you've got all three wavelets in phase there better than anywhere else. If we look at 5 wavelets, just add 2 more besides the 3 that I've already talked about. Again, the brightest fringe is at the center of the image plane because that is the one place that all 5 are mutually coherent. Everywhere else, some interference in a negative way is destroying the intensity, and all wavelengths are in phase at the center of the image plane, and so that is the brightest area. And you can see as you add more and more contrast enhancement, besides these 3 bright islands, there are lots of little side lobes that are dimmer. So that's 5 wavelets. If we go to 9 wavelets, the image becomes more straightforward in a way. That is the one place, again, where all those wavelets are in phase because they're equidistant from each other, is right at that point there. And all the wavelets are in phase there, and that is the main peak, but there is this set of banding on either side of that point. Now, if we just add all the wavelets together, this is the point spread function. This is going from 9 wavelets to an infinite number. And let's just go through the shape of this object now. All the wavelets are in phase at the center of the image plane. Light is concentrated in the middle of the image plane. All other fringes or side lobes progressively dimmer. In fact, you need enhanced intensity to see them, as shown in this very bottom horizontal picture. And most of the light is now seen within a cone. It seems like all the interference has left very little light outside of this converging cone of light that focuses on the specimen and then rediverges. This is an hourglass shape, and that comes about not through ray optics, but just through interference of wavelets. The width of the main peak is set by the extreme wavelets, the 2 on the 2 ends of that spherical cap, and that is set by the numerical aperture. So the size of the image for a very small point is related to how far apart those wavelets are. The farther apart they are, the more focused this object is, and that's why the numerical aperture is essential. So if we compare the effect of numerical aperture on the point spread function with high numerical aperture compared to low numerical aperture, you see a profound difference. With high numerical aperture, there's a wider separation between wavelets, which is possible because they're far apart. As a result, there's a small central peak, whereas with low numerical aperture lenses, only a narrow separation between the wavelets is possible, and so you have a broad central peak and less resolution. So let's now think about this in terms of what the image of a point looks like. So if we focus now not in the axial direction, but looking down on the surface of an image of that point right in the focal plane, the point in the specimen would appear as a small dot. This dot is called an airy disk because if you enhance the contrast, you find that the dot is surrounded by these fainter rings of light, which is the diffraction pattern of the point. This is the point spread function in one single plane. Airy is a name of a researcher, I think he was originally an astronomer, who saw airy patterns around stars and understood that this was an artifact of diffraction, not the fact that every star had rings around it. The PSF is a series of concentric rings, and larger rings have progressively lower, the farther out the rings are, the progressively lower intensity. And if you have to remember anything in light microscopy in terms of equations, it would be this, that the distance from the center of the airy disk, that center circle, to the first dark ring is 0.61 times the wavelength of the light, lambda, divided by the numerical aperture of the lens. 0.61 lambda over Na. If you want to carry around any fact about light microscopes, that's the one you should carry around because, as you'll see, that is the resolution limit of the light microscope. 0.61 lambda over Na is the distance from the center to the first dark ring. One can also look at the airy pattern in the not lateral direction, but in the axial direction, in xz, x being a lateral and z being the depth plane, and one sees that the airy pattern is now not a circle, but more an ellipse. And again, there are 2, if you enhance it, there are 2 dark spots in that direction, and that's a longer distance. It's determined by another equation, 2 times the index of refraction of the material between the objective and the specimen, so 2 times n, times the wavelength divided by Na squared. And for high numerical aperture lenses, this is sometimes around 3 times bigger than the XY resolution. So light microscopes intrinsically have slightly better resolution in the lateral plane than their ability to discriminate from one plane to another in the depth plane. So, can we use this to help us understand resolution in the light microscope? This 0.61 lambda over Na, the distance between the center and that first dark peak. There are, if you think about this, these are the numbers calculated for a high numerical aperture lens, a 1.4 numerical aperture lens with light at 480 nanometers. You can see that the lateral resolution, and I'll explain why it's resolution in a moment, is 225 nanometers, whereas the z-axis resolution is 861 nanometers. Not nearly as good. So how close is it possible for 2 point sources to be and still be seen as 2 points? This is basically the question of resolving. If 2 objects are close and you still believe they're separate objects, then you can resolve them. If they blend together, you can't resolve them. So here, for example, are 2 point sources, and they're moving progressively closer. There they are sitting on top of each other at the bottom, and they're far apart at the top. No one would disagree that there are 2 points at the top. No one would believe that this is 2 points at the bottom. How do we decide when these 2 points are resolvable? This is sometimes known as the Rayleigh criterion. It's an arbitrary criterion. It's not a generally accepted criterion that everyone says tells you the resolution, but most microscopists use the Rayleigh criterion, which is the criterion that is related to 0.61 lambda over Na, that distance. So that distance, as I mentioned to you already, is the distance between the center of one disk and its first dark ring. And if we look at these traces here, these are these 2 points that are just at the Rayleigh criterion apart. That's 0.61 lambda over Na. The center of this object is sitting right on the first dark ring of that object. If you look down here at an intensity trace, where the first one is at its lowest value is where the other one is peaking. And at that position, there is, maybe a little more than 20% of a dip in intensity between them when you add the 2 intensities. One can also make the Rayleigh criterion in the z-axis, where you go from the center of one to the first dark ring, to its first dark ring, and put the other object at that distance, and that again gives you a value where they dip about 19%. And these are both related, and this one is related to the other equation that I mentioned, 2n lambda over Na squared, whereas this is 0.61 lambda over Na. Now the value of numerical aperture is it makes those points smaller, so presumably the point spread function, by being smaller, allows objects to be closer together. And here's a classic example of this, a bunch of beads where they've been imaged with a low numerical aperture lens, a medium numerical aperture, and a high numerical aperture lens. There's no difference in magnification, but there's no doubt in C that you have a bunch of individual beads with lots of rings around them, but you still see them as separate. In the medium Na, it's a little harder to do, and with the low Na lens, it's just a big blob. You can't actually figure out what you're looking at all. I want to just say one last thing, which is important to realize, that if you want to get the resolution out of your light microscope, you not only have to understand what limits it in terms of the diffraction limit, but you have to sample the image at enough frequency that you can see those high frequency details. And this requires you to keep in mind Nyquist's limit. And Nyquist was named after a scientist, Harry Nyquist, who stated that sound must be sampled at least the highest frequency in the sound times 2. So it must be sampled twice the highest frequency to extract all the information from the bandwidth and accurately represent the original acoustic energy. So for example, the human ear hears frequencies up to 20 kilohertz. So a CD, if you have one, will sample at 44.1 kilohertz, so that you can hear that 20 kilohertz clearly. Phone lines pass frequencies up to 4 kilohertz, so phone companies sample at 8 kilohertz. So the sampling theorem says, and this is just the Nyquist theorem, a continuous function, for example, some banding pattern in an image, can be completely represented by a set of equally spaced samples if the samples occur at more than twice the frequency of the highest frequency component of the function. So to capture a function with maximum frequency f, whatever it is, whatever image you're looking at, you must be resolving it. You must be taking samples that are at twice that highest resolution, 2 times that frequency. And this is the Nyquist limit. And down here is just shown why you have to do that. If you have a banding pattern, and that red is sort of an area that's going from light to dark, and you only sample at the resolution limit, so you get 1 sample per wave of that light-dark cycle, you're going to end up with aliasing. You're going to end up with a pattern of light and dark that's going to not be the high frequency. If you want to see that high frequency, you have to have at least 1 sample from each peak and each trough. And I just emphasize this because most microscopists do very well. They get very fancy objectives, and then they fall down on the imaging side. They do not do Nyquist limited imaging. So for example, if the resolution limit is 0.61 over NA, and you want to see that resolution, you're going to have to sample enough so that there are at least 2 pixels between those two. So the Nyquist limit is 0.3 lambda over NA, and one has to either zoom the microscope image, use a higher magnification lens to make sure one matches the charge-coupled device or whatever digitizing device one is using for the image to make sure that the pixel size on the image is twice the limit due to the point spread function. This is all great. Sometimes, however, it's not enough. And I just want to end this by telling you that there are still things people can do if you feel you need more resolution than your microscope objectives can give you. One is that because it's 0.61 lambda over NA, if you use shorter wavelength light, you will have better resolution than longer wavelength light. So blue light or ultraviolet light will give you a sharper image than red light or infrared light. If that's not enough, you can keep going to higher index of immersion liquids because 0.61 lambda over NA, the NA term is related to the index of refraction times the half angle. The higher the index of refraction, the higher the resolution. So oil is better than glycerin, and glycerin is better than water, and water is better than air. And there are even some very esoteric oils that allow you to push into very, very high numerical apertures. They're stinky oils, not very easy to obtain, but there are things you can do. A confocal microscope, which many people have access to, if it's used properly, can improve your resolution by the square root of 2, by about 1.4. So that's something to think about. And if you can study single spots, you can localize them by looking at the center of the airy disk, and that can give you super resolution. And that arbitrarily high resolution has been used to track objects moving over time. And it is also the basis of one of the many new techniques known as super resolution techniques, optical nanoscopy, which I won't talk about today, but someone will probably provide you information with. So thanks very much.